Chapter 6, Part 2, SN2 Reactions. SN2 reactions are bimolecular substitution reactions. Bimolecular means that two molecules are involved in the rate-limiting step. So the rate of an SN2 reaction is equivalent to the rate constant times the concentration of the alkyl halide or electrophilic species times the concentration of the nucleophilic species. This means that this is a second-order reaction. So, for example, in an SN2 reaction, the nucleophile comes around from the back side of the molecule, meaning the side opposite the leaving group, and the electron pair of the nucleophile attacks the electrophilic carbon. This leads to an intermediate state where the bond between the nucleophile and the electrophilic carbon is forming, thus the dotted line, and the bond between the carbon and the leaving group has weakened. It's about to break. Also notice that in this image, the molecule has gone from being sp3 hybridized to something that kind of resembles an sp2 center, with the nucleophile and the leaving group on opposite ends. So then, once the leaving group leaves, as the arrow there represents, you end up with your new molecule where the nucleophile has taken the place of the leaving group. But notice that the stereochemistry has been inverted. Whereas previously the leaving group was on the right-hand side, now the nucleophile is on the left-hand side. Now, this isn't necessarily important in this particular example where all three of the other substituents on the carbon are hydrogen atoms. But if those were different atoms, the relative stereochemical designation would actually be flipped. So this is called an inversion of stereochemistry. So SN2 reactions are a concerted reaction. This means that the bond formation and the breakage occur in one step. So if we were to look at the reaction energy diagram of an SN2 reaction, what you see is the starting material going up in energy to that transition state. This is after the nucleophile has attacked, and neither bond to the nucleophile has been fully formed, or the bond to the leaving group has fully been broken. And then coming back down is when the leaving group is leaving. The difference in energy between the starting material and the transition state is the activation energy, and this is the energy that has to be overcome in order for a reaction to occur. There are two different possibilities here. You can have your starting material start off at a lower energy than your product, or your starting material can start off at a higher energy than your product, meaning that your starting material was more reactive and less stable than the product. Whereas in the other circumstance, the starting material is more stable than the product. So these two differences are the differences between an endothermic reaction, where energy has to be put into the system so that the product can be formed, versus an exothermic system where energy leaves the system as the product is formed. So let's look at the stereochemistry of the SN2 reaction in a little more detail. The nucleophile approaches the electrophilic carbon from the opposite side of the leaving group. This again is called backside attack. You're going to hear this phrase over and over in this chapter. So looking at the mechanism again, the nucleophile attacks that carbon, and in one step, the leaving group leaves, taking the electrons in that covalent bond with it, which is what creates the new lone pair on the leaving group. Notice that in our previous example, if we were to assume that the leaving group and the nucleophile had the lowest priorities, the substituents go from A to B to C in a clockwise arrangement, but in the new product, they would go A to B to C in a counterclockwise arrangement. So the relative stereochemistry has been inverted. This is called a Walden inversion. Now, please note that it does say that this is not necessarily an inversion of the absolute stereochemistry. So depending on the relative priorities of A, B, and C, and then also the nucleophile and the leaving group, you could go from an R compound to an R compound, even though the relative stereochemistry has been changed. The absolute designation might stay the same, depending on the overall priorities. You can picture this a lot like an umbrella in the strong wind. If you are holding an umbrella and you're in the rain, and you can picture the umbrella kind of like this. The nucleophile comes in, which is the wind in this example, and inverts your umbrella.